Welcome to Gradient Daily. Today, we're analyzing the mathematics of physical AI environments and why achieving accurate geometry requires collapsing an entire dimension. We are examining research from a team at the University of Tübingen and Shanghai Tech, who developed a novel architecture called 2D Gaussian Splatting. Navigation in robotics and digital twins depends on precise collision detection. For an autonomous drone or a robotic arm, a radiance field is only functional if it defines exactly where a physical object begins and ends. Standard 3D Gaussian splatting fails at this task. While the pipeline excels at generating realistic images at high speeds, the underlying physical geometry it builds is chaotic and unusable for physics calculations. This comparison illustrates the core issue. On the left, traditional 3D GS produces a smooth surface texture, but stripping the color reveals a lumpy, distorted wireframe underneath. On the right, the new 2D Gaussian splatting method yields that same visual quality, but reveals a perfectly smooth, flat mesh. To achieve these physics-ready surfaces while maintaining real-time rendering speeds, engines must abandon 3D volumes entirely. The solution is to collapse the primitives into 2D planar disks. The fundamental building block of recent real-time radiance fields has been the 3D Gaussian, a soft, semi-transparent volume of density and color. The structural flaw in using volumetric blocks is best understood by trying to build a perfectly flat wall out of water balloons. From a direct distance, they might look cohesive, but as the camera shifts to an oblique angle, the bulging, rounded edges of the balloons are revealed, breaking the illusion of a flat surface. A 3D Gaussian relies on a 3D covariance matrix, distributing density across 3 spatial dimensions. Overlapping these forces them to overfit to specific camera angles. Straight on, they approximate a solid block, but shifting perspective 45 degrees exposes the bumpy, disjointed structure. The resulting geometry is a mess of floating density blobs. The model is essentially layering thick fog to fake a hard boundary, resulting in a total lack of intrinsic surface definition. You cannot build a mathematically precise flat surface using inherently volumetric building blocks. The architecture of 2D Gaussian splatting removes this bottleneck by changing the core primitive. Instead of water balloons, the geometry operates like a tiled roof. A complex, pitched 3D shape is constructed entirely by overlapping, rotating, and scaling perfectly flat, two-dimensional shingles. Shrinking the traditional Gaussian z-axis to 0 collapses the volumetric blob into a flat 2D circular disk. 3 parameters control this. A center point dictates position, a normal vector controls face direction, and a 2D bounding box represents the covariance spread. Because the third dimension of density is gone, the primitive natively models surfaces intrinsically. A specific coordinate is either making contact with the disk or it isn't. By forcing the model to operate strictly in 2 dimensions, the math guarantees geometric flatness regardless of the camera angle. Operating in 2 dimensions introduces a specific mathematical challenge. An infinitely thin 2D disk disappears if the camera looks at it perfectly edge-on. Think of shining a flashlight onto a severely tilted canvas. To calculate light dispersion without shadow distortion, you must measure the beam's exact intersection angle. The standard projection math used in 3D GS fails under these conditions. When viewed from sharp side angles, the equations cause the 2D disks to visually tear or disappear entirely from the render. A Ray-Splat intersection mechanism resolves this. As the camera rays strikes the tilted 2D plane, a glowing dot registers the intersection point, projecting a stable line back to the screen. This stabilizes projection math, ensuring accurate density calculations from steep angles. Perspective-correct rasterization forms the vital mathematical bridge, allowing infinitely thin surfaces to maintain stability inside the 3D rendering pipeline. Even with stable splatting, the rendering engine requires parameters to force these individual disks to align into a cohesive mesh, otherwise they drift apart. 2 regularization terms bind the mesh. First, depth distortion minimizes intersection depth variance along a camera ray, condensing scattered primitives into a dense surface. Second, normal consistency rotates the normal vector into parallel alignment with the depth map gradient, ensuring correct physical direction. The team trains these models on standard datasets like MIP-NERF 360, initializing them with COL-MAP point clouds. This provides a baseline point of reference to test the system's ability to recover high-frequency, complex textures. Without these two specific regularization equations, the geometric points remain chaotic confetti. With them, the individual disks bind securely into a solid, extractable physical mesh. 2D GS achieves higher geometric accuracy than established methods like NUS. By swapping thick 3D blobs for flat 2D disks, the engine stabilizes the optimization of the underlying mesh while maintaining real-time frame rates. The paper does contain critical limitations, primarily in its heavy reliance on the quality of the initial point cloud data. Because the 2D disks are infinitely thin, they lack the volume to easily bridge wide spatial gaps. If the initial Colmap point cloud is sparse, the 2D model struggles to span the empty spaces in ways that fatter 3D blobs naturally cover. Future research directions will likely explore solutions for sparse initialization, while testing how effectively 2DGS scales across highly reflective surfaces or dynamic moving 4D scenes. To summarize the findings, first, 3D volumetric blobs lack the math to define an intrinsic surface. Second, collapsing those primitives into 2D planar disks allows for native surface modeling. And third, applying perspective-correct rasterization exacts physically accurate meshes. Thank you for watching Gradient Daily. Subscribe, and we'll see you tomorrow for our next breakdown. 2D Gaussian splatting provides the mathematical foundation required for machines to physically interact with reconstructed environments.